Okay, section 2 picks up right about where section 1 left off. So in section 1, we defined probability. Well, we actually defined probability three ways, the most important one being the classical or the theoretical probability. And that's the number of simple ways our event could happen. So the number of simple outcomes that make up our event divided by the number of total possible simple outcomes of the experiment. Let's just jump in and do an example dealing with the theoretical or the classical probability. So let's say, what's the probability that a couple has three children and two of the children are boys, one is a girl? Under the assumption that every child is either a boy or a girl and that they're uh, both boy and girl are equally likely or have a 50% probability. It's not 100% accurate, but for the purposes of this example, let's just simplify it. So, um, our experiment or the procedure is having three children. And so, there's the experiment, three kids. And the outcome that we're looking for is two boys and one girl. So that's our outcome. So we could call that A. And we're looking for the probability of A. What is the probability that upon having three kids, two of them are boys and one is a girl? Well, let's think about all the possible outcomes, possible scenarios here. So if you have three kids, you could have all three boys, you could have two boys, you could have one boy, you could have no boys. So let's think about this in the context of the definition of classical probability. Consider all possible events. Count all simple. This in green. This should say outcomes, not events. Count all simple outcomes corresponding to the event, and apply the traditional formula or the classical formula for calculating the probability. It comes down to counting, and whenever you're calculating a probability, you have to count two things: the number of ways, the number of simple ways your event can happen, and the total number of simple outcomes possible from the experiment or from the procedure. So we have four outcomes here. The one in red is the one we're looking for. That's our event. So you could have three boys, like I said, three boys, two boys, one boy, or no boys. Just be careful here. It's very important you make the distinction between a simple outcome and a compound outcome. We need to always count simple outcomes. And in this case, we cannot say the probability is 1 out of 4 because these four outcomes are not equally likely. Two of them are simple, so I'll use green here. That's a simple outcome. It can only happen one way. That's a simple outcome. It could only happen one way. So all boys, meaning a boy, then a boy, then a boy, or no boys, meaning a girl, then a girl, then a girl. Two boys and a girl, well, that could happen multiple ways. We have to count how many ways each can happen. Now, with small numbers like this, it's it's not too inconvenient to just list them out. We don't need to know what they are, but listing them will allow us to know how many outcomes there are. So this is the event we're looking for, and that event consists of three simple outcomes. Two boys and a girl. That girl could come first, the girl could come second, or the girl could come third. So when we're calculating probabilities, we need to count two things: the number of ways your event could happen and the number of outcomes in your experiment. So, and this is a term I briefly mentioned in the first section's notes, the sample space. So this green box here, the list of all possible outcomes of your experiment. That is this. We call this the sample space. We could restate the definition of classical probability and say the probability of an event happening is the number of ways the event could happen divided by the size of the sample space. Size of the sample space is the total number of outcomes possible from your experiment. In this case, our list is 8, so the size of our sample space is 8. Probability, therefore is 3 divided by 8. The probability of having 2 boys and a girl is 3 divided by 8, or about 37.5%. Now, like I said, with small numbers, we don't need to know what these 8 outcomes are. We just need to know that there are 8 of them. And with larger numbers, it becomes logistically impossible to count by listing. So we're going to develop strategies to count how many outcomes are possible in some systematic way or some formulaic way without actually listing. But let's consider this example. We have a club with 4 members: Alice, Bob, Charlie, and Dave. Conveniently A, B, C, and D. In how many ways could they choose a 2-person team to represent the club? Well, the numbers are small enough here that we could just list them all out. We could pick Alice and Bob. We could pick Alice and Charlie. We could pick Alice and Dave. We could pick Bob and Charlie. We could pick Bob and Dave, or we could pick Charlie and Dave. I think that's it. Yeah, there's only 6 ways that we could pick a 2-person team to represent this club. Now, let's change the problem up a little bit. In how many ways could they choose a president and a vice president? Well, now order matters. And we're going to have to make this distinction in the next few sections when we're counting. Does order matter? Does order not matter? There's going to be a different formula for each case. In this case, still the numbers are small, so we could still count by listing. The difference here is Alice and Bob is different from Bob and Alice. So if Alice is president, Bob is vice president, well, that's a different outcome than if Bob is president, Alice is vice president. So in the last slide we had 6 groups of 2, and each group could happen in 2 different orders. So there should be 12. If we were to make this entire list, there would be 12 ways to choose a president and a vice president. But now if that club has, let's say, 20 members, and we're choosing a president, a vice president, a secretary, and a treasurer, well, there's a lot of ways this could happen. And in fact, there's 116,280 ways this could happen. So this is not something you would want to list one by one to count. That number, 116,280, we'll calculate that later. That's actually a result we'll see from a formula in the next section, in section 2.3, or sorry, 3.3. Okay, so, and this just sort of summarizes what I've just been talking about. Since calculating probability comes down to counting, and when the sets are really, really large, counting by listing is no longer feasible or logistically possible. Okay, so the first tool we're going to use here is the fundamental counting rule. And what this tells us is that for a sequence of events or a multi-step procedure or experiment, the number of ways that the entire event could happen is equal to the product of the number of ways each step could happen. So if we could generalize this is the fundamental counting rule for a sequence of 2 events. So if the first event could happen in m number of ways and the second one could happen in n number of ways, then the 2 events together could happen in a total of m times n number of ways. I think it might be easier to see this through an example. So let's say, how many license plates are possible if each license plate consists of 3 letters followed by 3 numbers? Okay, so it's for one single license plate. You could think about this as a 6-step procedure. Pick the first character, pick the second character, then the third, then the fourth, then the fifth, and the sixth. So we could look at how many ways is each step in this procedure. How many ways could each step in this procedure be done? So for this first problem, how many license plates are possible if we have 3 letters followed by 3 numbers? Well, if you think about this license plate, 6 characters. Well, in how many ways could you choose position 1? Well, position 1 has to be a letter, so you have 26 ways you could pick the first position. Position 2, also a letter, so there's 26 ways that could be done. Position 3, also 26 ways. Position 4 has to be a number, so that's anything 0 through 9, so that's 10 options there. Position 5 is a number, 10 options there, and position 6 is a number, 10 options there. So letter, 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 number, 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 and to find the total number of possible license plates, the fundamental counting rule says we multiply all of these numbers together. I don't have my calculator open, so let me just pop that open real quick. Okay, so 26 to the 3rd power times 10 to the 3rd power. So according to the fundamental counting rule, we have 17,576,000 possible license plates. Now we could just adjust this approach for the second problem. How many license plates are possible that have no repeated letters or numbers, so no repeats? So let's get rid of this. No repeated letters, meaning we pick a letter for position 1, and there's 26 of them. Now 1 letter is gone, which means we have 25 options for position 2. Now we've chosen 2 letters, so there's 24 letters left for position 3. Now onto the numbers, we have the digits 0 through 9, so we have 10 options there. 1 number is used, so we have 9 options for position 5, and finally 8 options for position 6. So whatever this turns out to be on the calculator, 26, 25, 24, 10, 9, 8. Okay, and when we have this situation with no repeats, you see this, we're just incrementally, progressively going down like 26, 25, 24, or so on. I want to introduce notation you may have seen before, possibly, possibly not, factorial notation. This is basically just an abbreviation for repeated multiplication. So the factorial symbol is the explanation point. So this n explanation point, this is read n factorial. It basically means for any number n, you multiply all the numbers from 1 up to n. And in the special case of 0 factorial, we let that equal 1, so there's no contradictions in any of the formulas. For example, 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. If you have a graphing or a scientific calculator, there should be a factorial function or a factorial button somewhere on there. Now, according to the fundamental counting rule, factorials come into play when we're arranging distinct objects, distinct meaning different. So for example, in how many ways could we arrange 7 objects? Let's say you have 7 boxes, 7 distinct colors. How many ways could you stack them vertically? How many different orders of colors can you create in a vertical stack? Well, just like in the last problem we did with the license plates with no repeats, we have 7 options for that first box you place, and then once that box is chosen, there's 6 options for the second box, and then 5 options left for the third box, 4 options for the next, and so on and so on. So the number of ways we could put 7, just in this case I'm saying colored boxes, but they could be anything. The number of ways we could take 7 different objects and rearrange them in different orders should be 7 factorial. 7 times 6 times 5 times 4 times 3 times 2 times 1. This is a direct result of the fundamental counting rule. So that number 7 could be anything. We could generalize this and say if you have n objects and they're all different, they could be rearranged in n factorial different ways. We'll use this factorial notation a bit, especially in the next section when we develop the two formulas for permutations and combinations. Okay, this is just a restatement of the fundamental counting rule. It works for more than just two steps. So for any a sequence of any size, like we did with the license plate, so that was 6 steps, a 6-step procedure. Okay, that does it for this section. The next section will use the fundamental counting rule. We'll use factorial notation along with the definition of probability, and we'll develop formulas for counting large sample spaces and counting the number of simple outcomes of events that have a large number of possible outcomes, more than are possible to list. Okay, that's it for now.